Hey there, Jim Gavigan, Industrial Insight. What you're about to watch is a conversation between Paul Sheramato of Pattern Discovery and myself talking about the latest release of Compression Insight 3.0. Paul's going to give a demonstration of the software. What you're going to find is, even with my video editing, and I did my best with it, there are some times we had some technical glitches with Paul's internet connection. You see, he lives in Toronto, and there was a major snowstorm that day that we recorded, and he wasn't able to get to the office to his high-speed connection. So we had a few little glitches here and there, but please put up with it. It's some really great content and a tool that I really believe is valuable. Hey guys, Jim
Yep.
Gavigan, Industrial Insight, here again with Paul Sheramato from Pattern Discovery. And this time we're going to give you a little more meat. We're actually going to let Paul show you the software that they've developed over the course of the last 8 years and show you actually the improvements they've made. And I'll probably interject a few times here and there because I'm really excited about some of it, and some of it I've used, and I'm really excited about the improvements. So Paul, take it away.
This is Compression Insight. It is fully integrated with the OSI Soft Pi system. We can include tags. So when you're looking to do analysis on tags, we will actually invoke the Pi SMT tool. You can select from that SMT tool. It will promote the tags that have been selected for analysis in Compression Insight. As we described or discussed earlier in the previous sessions, we actually set compression. We set the exception setting to 0 in order to be able to collect the raw snapshot. So it'll give you information regarding that that whole process. But so totally integrated, we can select right from the system here, or we can include tags from a clipboard, which were imported through the Pi Data Link service, and just pull those right into Compression Insight as well. So this is what Compression Insight looks like. So in this particular case, I've got about 76 tags that I've included for analysis. This is all simulated data, so some of it I don't have an actual live Pi system to a facility at this point, but anyway, this is simulated data. It'll give you a feel for what we're able to find, and certainly we'll have a greater discussion about data fidelity and the storage elements storage requirements that we're talking about. So on the left-hand side here is a navigation pane, which will basically tell you when we've collected sufficient number of snapshots to be able to make a statistically valid recommendation. And so these are categorized into, so all of these in this ready category, we have already made recommendations. We are continuously making recommendations, and it all depends on the scan rate that we're receiving data. So typically a 1 second scan rate will take us about 1 day to make a statistically valid recommendation and promote that through to be in this ready mode. What you're seeing here is the summary screen of all of the tags that are in this ready mode, or ones that we've made the analysis and they are ready for review. We can look at, there's a number of ways that you can look at it. There's a whole bunch of information that we can present in the summary screen. You can, I've only got a couple of things from an attribute perspective, but you can turn on any number of different things like the configured exception and compression deviations as an example. Those will show up in the summary. I could turn on the recommended compression and exception deviation so that you can now begin to compare those side by side. If you wanted to, you could move these columns around. I'm going to just reduce some of this information here for now, just so that we have a little clearer view in terms of what what we can look at in the summary screen here. You can also sort all of this information by, what are the things that I'm most interested in. So in this particular case, I've sorted on archive. I can sort on archive fidelity simply by clicking once. I can see tags sorted based on, this was the archive fidelity, this is a recommendation. So those tags that are at 100% that we talked about earlier, these are all tags that we would consider under-compressed. And then basically the recommendations next to that. And then the same way, if I look at tags that are over-compressed in the archive, we can sort them. I'm going to go into a little more detail on these, but you can see that the recommended fidelities based on this new optimization algorithm have really zeroed in on getting the highest fidelity possible with the least amount of storage that we can achieve. So we're improving data fidelity significantly in most of these cases, other than obviously when you get into the 100%, or the ones that for zero compression, we actually reduce the data fidelity. But we'll go into a couple of those examples. I wanted to show you one that we used in the previous session. We showed you a little bit about this particular tag. In the summary, if I double click on that specific tag, I will come up with this detailed view. And the detailed view provides you that graphical feedback of information or data that's actually been captured. I can zoom in here a little bit more. And you can see here that this is that red line that we talked about earlier. This is the archive data that would have been stored if in fact the original exception and compression deviations were applied. And the calculation that we made, this fidelity measure, the data fidelity measure, we actually calculated the fidelity is only about 23% of the original snapshot. So in this case, up in this right-hand corner, you can see I've got about 220,000 snapshots that have been collected. We're only saving in the archive about 993 of them, which translates into an information measure of only about 23.4%. We have now come in and using, again, this new optimized data fidelity engine, we have created we have made a recommendation for an exception and compression deviation, and we've improved the data fidelity to 94.9%, but we are consuming a lot, we're consuming more data, but we've only increased the archive count from 0.5 to 22.4. So versus what we would have been collecting with raw snapshots, which would have been 100% of this 220,000, we're able to achieve 94.9% data fidelity with only 49,000 of these 220,000 points. So I'm going to show you what that looks like here. So if I'm going to turn off, so there's the snapshots. So I'm going to turn off recommendation. You can't really see the recommendation because it's in behind the snapshot values. So what I'm going to do is turn off the snapshot values. So if I turn snapshots on and off, the green line that you see here is actually our recommendations. And so as I toggle between the snapshot values and the recommendations, you can see that the recommendations are very closely mirroring the actual characteristics of the original signal or the snapshot values. And by comparison, you can see certainly the difference between the archive values, what they would have been, and now what our recommendations are. So coming back, it's this optimization, which is really the really new enhancement and feature to the compression insight algorithm. So we've now been able to then zero in on the lowest amount of data volume, but the highest quality of data coming into the archive. So that was an example of a tag which we would have considered over compressed based on the original configuration settings in the Pi system. Let's go down and let's have a look at a tag that now we would consider undercompressed. So this is information. So this is we're already receiving 100% archived data. I'm going to just go into this particular tag. And you can see that the original archive settings were 0 exception and 0 compression deviation. So that translates into 100% data fidelity. We're storing about 180,000 of this 220,000 tags. There's still a very little bit of compression going on because it's retaining or it's not retaining exact redundant values. That now when you look at the archive versus the snapshots, right? So there's the original snapshot values. There's the archive values overlaid directly on the snapshot values. So we are collecting virtually or 100% of we have achieved 100% data fidelity. But now, when I now go and I have a look at our recommendation is saying we're recommending these exception and compression deviations, which is going to reduce our data fidelity somewhat. It reduces it in this particular case from 100% down to 93%. But we've improved the archive ratio from a total of 81% down to only 11% of the total volume of data. So we're only storing 23,000 of the 220,000 data points, but we're getting we're getting exceptional data fidelity characteristics here. And I can show you that now. What I'm going to do is I'm going to turn off the archive. And what I've now done is I turned on the recommendations and snapshots. And so if I look at this, there is the recommendations, there's the snapshots. And if I zoom in closer, and I will try and zoom in as close as I possibly can, it's almost difficult, unless you zoom in really, really tight, it's almost impossible to determine or see the difference between the snapshot values and the recommendations. So
yeah, this is something similar what I used to do when I would convert it to manual, which is that little button down on the right. Is, you know, I would see the little, like on some of the spikes, I would see where it would kind of level off and do different things. And I would go in and zoom in, and I might even send that to the customer and say, hey, you know, is this the difference in this measurement meaningful, or is it instrument noise? You know, that would be kind of my, you know, my thing. But you just saved me a whole lot of work, because I used to do this manually.
Right.
And it was kind of interesting because I guessed about 17,000 or 18,000 points or something like that, you know, before. That was kind of interesting that I was pretty close on that number. I just kind of guessed. I threw it out.
Well, this was really a request from a number of different customers.
Yep.
who have both a variety of tags that were overcompressed, and so we did a really good job at that. But then they had a whole slew of tags that they considered undercompressed, and they needed a much more automated method of evaluating and getting to the end result sooner than then. And again, we kept the manual mode in here, and I can actually, you know, if I convert this to manual, it'll bring up a slightly different user interface. The signal stays the same, so all of that same information that we had originally in the detail screen before stayed the same, but I could literally go in now. Let's say that I'm not, you know, this seems pretty good, but maybe I can relax the settings even a little bit more. And so I could do what if scenarios now. And if I went in here and say, okay, well, what if I relax this to, say, an 80% data fidelity target? And again, I don't think I'm going to do this for an awful lot of tags, but still it gives me the capability of going in and having a look at what a custom target fidelity reading would be.
Yeah. So Paul, take that down to like 60%, and then that way, because I want to show people like that, this is how it changes this custom recommendation. So yeah, let's go ahead and do that.
Okay.
And then zoom in, because then you'll be able to actually see it.
Right. So it took a couple of seconds there, but what the engine is doing is actually taking this information measure that we have established as data fidelity, and we're reverse engineering that so that now we're establishing where on that curve this point actually fits at a 60% data fidelity rating. And so I'll zoom in here. I'll turn off archive first and zoom in on a portion of this. And let's zoom in a little bit more. And so now you can see, so if I turn off snapshots in the custom, so there's a there's the raw snapshots, and here is our custom exception and compression setting. That's the representation of what they would be at these settings here. So we're losing some fidelity, again, depending on exactly. In this particular case, we're running somewhere between 27 and 50, whatever this is. I'd have to look at what that snapshot actually is, or what that data point is. But you can see here that what we've now done is we have actually reduced the amount of data that we're archiving by a factor of about 12% or 13% here. So in this particular case, where we've established a specified fidelity of 60%, we're only saving 5,300 of the original 220,000 raw snapshots. Yeah, but it does show up in data fidelity, right?
Yeah, I think this is kind of important, because you may have, let's say it's a level transmitter that doesn't change that often, that's getting scanned too fast. You might want to detune it a little bit. Or, if I have some kind of a high-speed position sensor or something like that, I may want to even up the fidelity from, what you've recommended, because you do a great job, right?
Exactly.
There may be specific use cases where I need to detune or tune up, a particular point. So it's important that this stays.
Now let's go in and just have another quick look at that tag that I was that we had up before, and do exactly the same thing. So in this particular case, we've actually we're achieving 94.8% with only 22% storage, and I can convert that to manual again, just as another example here. And if I really wanted to fine tune this and I wanted to get it a little bit higher, but I still don't want to collect the raw snapshots, I want to get it a little bit higher, so I can go in and start to play with this. And let's say I took it up to 97% data fidelity, right? And so again, these are some of the what-if scenarios that you can perform, depending on the specific nature of the instrument that you're or the process that you're trying to manage here.
Yeah. So click on recommended down there. Now let's see what the difference is. So you would have recommended 4,828 points. And yes, by saying, hey, we want to get a little better, we want to get to 97% fidelity, you'll get about 910 more points.
Yep.
And so you can see what your specification deviations go to. They go to 0.003 and 0.005. You could even click that radio button and say, hey, I want the deviation to be 0.0025 and 0.0001, right?
Exactly.
So you can do with that, and then it'll calculate the fidelity that you would achieve. So you can kind of really, from whichever angle you want to look at it, you can do some very specific tuning.
Exactly. So, but again, it shows you the power of this data fidelity measure that we've come up with. Being able to measure the amount of information that you're actually archiving in the system based on either the original settings or the new recommendations or whatever target fidelity that you want, really gives you that feedback that has been missing in terms of, what does it really mean to me in my process, and how good is this information going to be in terms of the value that it will create. So.
Yeah, and the nice thing is you can, like if you want to show this to someone, you can hit save chart and it saves it, what is a JPEG, if I remember right?
That's right. And you'll save the chart. I can hit that.
So if I'm an engineer and I want to go to operations and show somebody like, hey, here's what we were, doing versus here's what we are now, because a lot of times, this video, probably the people that are going to watch this are going to be people who are highly technical, and care about all that stuff. And management's going to go, well, why is this even important to me? And you can literally show them that beam me up Scotty thing that we talked about in segment 2 is, right, hey, this is what we were collecting and this is what we were storing versus this is what we're going to do now. So our ability to be accurate in our recommendations based on all the things we're doing with our data now is going to be much greater because the data coming in is going to be more accurate. And I think that's going to be a real eye opener. So I'm glad you allowed that. So now I'm going to play straight man for just a minute. What happens with those tags that are like really, really noisy, or they flatlined or something like that? How do you guys handle that?
Yeah, that's a really good question. And one of the things, so a noisy tag, when you look at a noisy tag, a noisy tag is very difficult to compress because it's changing so dramatically from 1 second to the next that the compression algorithms, whether it be the boxcar or swinging door compression algorithm, is really having a tough time keeping up with those quick variations. And so a noisy signal is exactly that. You're collecting so much information on a per second basis, or it's changing so dramatically on a per second basis that the algorithms don't have a chance to keep up. And so because we are actually doing an evaluation of the observed data, so what we're seeing, what you see is what you get. And so we're saying, you know what? We're trying to do a recommendation here, but we're seeing evidence that this may be a noisy tag because it is very difficult for us to hard to compress because we can use these analytics any way that we want. And so we created a whole new category of information that is then summarized, and we have these tags that we look at and we consider them hard to compress. So simply using compression changes or changes in the deviation may not be solving the problem associated with this particular tag. It may be a calibration issue. It may be a noise issue that's related to the communications problems or whatever. But what we're suggesting is that these tags we can still do a reasonable job of compression on them, but it may require some subject matter expert to go in and have a closer look. And so, I'll give you an example of that. So if we go in and have a look here, here's a tag that we've labeled or flagged as hard to compress.
I've never seen anything like that in any enterprise system. What are you talking about?
Yeah, well, this is way too common an occurrence for sure. It's the real world though, right? This tag is, so this tag is really difficult to compress, and you can see that in spite of an exception in compression deviation in the original archive settings, the original configurations of 1.8 and 3.6, it's changing so quickly that we're actually achieving 60% data fidelity because the algorithm is trying to keep up. And so we still come in here and make a recommendation, and we can still improve the data fidelity on this, but we're saying that this may not be something that you necessarily want to to do with a data fidelity measure.
Yeah,
So, or with a may not want to solve this problem through a compression analysis.
yeah, this may not be a pi system problem. It may be a sensor issue. It may be a controls issue. It could be any number of things. But you've given, I mean, you really think about, what you've done is you've given the non-technical, non-subject matter experts in the field the ability to go back to their subject matter experts and say, hey, this signal doesn't seem to look right. Maybe it's reality, right? Maybe that this is just the way this signal is and this is what you expect. But you find a way to add value to people who are, not necessarily subject matter experts and not necessarily incredibly technical on the process, and you give them the ability to say, here may be some issues that you want to go look at. Here's a signal that's completely flatlined. It's gone flat. Or here's one that's incredibly noisy. And they may say, you know what? We didn't even know because we don't look at it every day. We look at it only when there's a problem.
There's so many examples of that. As a matter of fact, that's exactly the way one of our customers is using the system today. So they have their Pi system admin folks who are managing the OSI soft system and the Pi archive, and they're now challenged, or their job is to do this initial exercise of tuning, but they're able to send back this wealth of information to the process engineers, and rather having those process engineers look at every single tag, they look at the tags that have been flagged or the tags that they want or that the administrator sees value in changing and provides the evidence at the same time. Yeah, so we've reduced the amount of resources and effort that requires to get to this stage, that's for sure. What you're seeing is literally a flat line. And so, should a flat line actually, is this the actual characteristics of this signal? I think in one of your previous videos, Jim, you had shown where, you had a case where a level gauge or a temperature reading, I'm not sure what it was, but it actually had flat line based on a problem with information coming from the interface. And so these are all useful pieces of information to tie together to say, hey, am I really getting the information that's being stored? Is the information that's being stored in the archive, A, what I'm expecting, and B, does it match with what we're observing in this analysis? We've added a number of different pieces of information regarding, little things, and it doesn't sound, this has certainly got nothing to do with compression per se, but one of the pieces of feedback that we got was, they wanted us to show the engineering units. What are the engineering units associated with these tags?
Yep.
And one of the things that we discovered is that people had misconfigured the engineering units, or they were using mixed mode between Fahrenheit and Celsius or whatever.
Yeah.
And this was a way to identify those things very quickly, or whether engineering units were actually not configured whatsoever.
Yeah.
Again, just little things, not necessarily related to compression, but very valuable when in terms of considering the quality of the data that you're putting into the archive and the end uses that you have for that data is really what our major concern is and criteria.
Yeah. So what's the performance and probe things on there? Continuing to play straight, man.
Yeah. So so you can look at I've got these are the flags that I've already got on, but you can look at for instance, we make an estimate of, based on the original archive fidelity. I've just turned on archive storage. The archive storage and the annual storage savings, these are values that we estimate on an annual basis. So we're just making an estimate of this particular tag FIQ 051.
Sure.
So it's what this is saying is we've estimated that this tag, given the original configuration settings, would store about 358 megabytes per year.
Here's a contrast. If you guys will recall from the first video, I was telling you stories where we were pulling 1 month of data, not 1 year, 1 month of data, and it was a half a gig. It was 500 megabytes. So you think about that, here's one that you're getting an observed scan rate of basically a third of a second, but by proper tuning, it's more like 358 meg a year versus half a gig a month, right?
Right.
So, I mean, that's a pretty big difference. I mean, you can take really high speed data that's quality data, and, you can still save a tremendous amount, of information and get all the data fidelity you want without having to store everything. So
Exactly.
it's really important. So talk to me about this probe thing. I think it's kind of funny. I think you and your developers actually probably had some issues with this because I lean in your camp on this, but go ahead and explain what this means, because I do think this is important, and people are probably going to poke at you a little bit, with this one. And I could see this name changing in the
yeah, I do too.
but hey, the developers put it in there, and it's an important piece of it. So talk about it a little bit.
It really is. So I'm gonna turn on these headings here. So I'm going to turn on probe curation.
I think what's really kind of interesting too is the observed scan rate, the observed span, and the observed zero. So you think about it, like I've had some customers come to me and they say, we have a really kind of wide range. Like we may have a temperature sensor that's like, ambient temperature to 1500 plus degrees, but the normal operation of it is from like, 1300 to 1550, right?
Yes.
That's normal operation. That's where I really need to do my tuning. So I think, for those kind of people where they really are like, I really want to tune this tag around like where it normally operates. That's actually kind of an important piece, because you'll say hey, we started, this, X time ago, we've collected this many points, and here's what we're seeing. And that may be a clue to a process engineer or subject matter expert to say, hey, something doesn't look right here, or no, don't take that recommendation yet because that process is out of whack. I can see that process must be down because that's not the observed span or zero that I would expect. And I know that process is down today, so let's not take that recommendation yet. So I think that's pretty important. So talk about the probe stuff.
Well, just to elaborate on that a little bit, Jim, is that so because we are using and we're doing an evaluation based on what we observe, there's a whole bunch of things that we can. So besides data fidelity and compression and exception, there's all kinds of things that we observe. We observe what the actual scan rate is coming from the interface, and so if it's different than what they're expecting, that's another clue as to whether or not the system is working the way that, not necessarily the PI system, but is the system working the way that they thought it would. And the observed span is really an interesting one, because we've seen a condition or a case where the configured span was set between 0 and 100, but these observed spans were significantly different than 0 to 100. And that has a big impact on the compression and exception settings, especially if you're using a percentage of deviation.
Yep.
And so these things became very obvious very quickly because of this observation. The other thing, and kind of coming back to this probe issue, is I've turned on the probe start, duration, and update. And so these three columns tell us when this when the analysis was started, so this is the compression analysis that we're doing in Compression Insights. So the analysis engine started performing or started working at this probe start. It's been running for X amount of time. It's been running here for, in this particular case, I started this one, it's been running for 2 hours and 2 minutes or whatever. And the last time it was updated was, you know, at one, in this particular case, it was 1:42. The individual who is actually performing this analysis can now look and say, geez, this thing was started, I've only collected X number of snapshots. So, you know, I look at this snapshot count, and again, this is all artificial data that has been data generated. But what you see is that the snapshot counts are perhaps nowhere near what they had expected to be receiving. And therefore, and so the longer that you leave, obviously the longer you leave these tags in for compression, or for analysis, you're going to be collecting more and more snapshots. But what happens when there's not enough snapshots being collected, right, for whatever reason? And it points out two things. The first thing it points out is that maybe this tag isn't worth compressing at all, because I'm simply not collecting sufficient numbers of snapshots that would make it worthwhile compressing in the archive, or it's significantly different than what I was expecting. Maybe somebody should have a look at this particular tag and see what's happening at the interface. And so it pointed out those two things. In a real world case where you're doing, you know, thousands of tags here, some of this information becomes extremely valuable for fine-tuning the tags, both either in the archive or considering what needs to be done outside the PI archive.
Paul, I'm going to kind of issue you a little challenge here. We touched on a little bit the last video, and then we ended up talking about it off camera. You know, but literally anyone who is doing data collection or IIoT, you know, like, you know, right now, if you look at both of our work, it is primarily centered around the PI system, because that's something that we both have kind of, quote unquote, grown up around doing, right?
Right.
But literally these kinds of techniques, you know, I think are going to be invaluable for everyone, you know, no matter what, you know, if they're a Wonderware user, IP21, you know, they're piping it to Amazon, you know, they're Canary Labs, you know, whoever and whatever system they're choosing. I think, you know, your tool here as kind of that first pass filter of, am I sending legitimate data on to whatever data collection engine that I have? I mean, to me, you have made it much, much easier for even a non-technical user, a non-process expert, to both have a legitimate and easy conversation with the process experts and saying, hey, here's where I think we're missing the mark. But then also take some physical pictures, you know, and do some quick explanations for, you know, executive management to say, look, you know, if you guys are off running around doing all these advanced analytics or wanting all this stuff, but here's the real thing that's going on at the ground level. And if we don't get this right, all that's going to fail. And you can literally break this down to them and say, scientifically, algorithmically, this is how we can take these measurements and do these things. And this is how we can ensure that our data quality is going to be good, without us sitting here having to stare at it all the time and put a full-time person on it. I mean, is that accurate? Is that?
Well, with one caveat, and the caveat is that the OSIsoft system has been, was developed, their compression, the algorithms that they use for compression, with some fine tuning of the boxcar and swinging door algorithms, those are the ones that OSIsoft uses for compressing the data that goes into the Pi archive.
Yep.
So what we did in terms of evaluating archive signals now is we used the exact same algorithms. We worked with OSIsoft on this. We used the exact same algorithms with the same modifications that they made to the boxcar and swinging door algorithm to be able to recreate the archive values. So that's how we can do the comparisons.
Gotcha.
We could do exactly what you're saying for any data historian by simply whatever means they set exception to 0 in those data historians. We will get those raw snapshot values. There is no question. What we don't have configured in our system at this point is the actual either algorithms or modifications that they've made to whatever algorithms that will give us the information that we're looking for relative to that specific archive.
Yeah, I got
I
you.
don't know if I explained that correctly or not. But
That makes sense. I mean, you think about like, AWS or Azure may not have any kind of a compression algorithm. It's just simply, pipe the data to me, right? So
well, they want as much data as they can get.
Oh, of course they do, right? Because
Sure.
they're going to charge you money for it, But I think what I see and kind of where I was going with it is there's a need to scientifically come up with a way to say how much data do we really need that's actually information, and how do we kind of fine tune that data pipe and what's flowing through it. You're right. The end system is going to limit kind of how that can happen,
How it gets applied.
how
Yes.
it gets applied. But
Yeah.
I just think this is a really important kind of a topic, because so many people are going to pipe, just like what we're doing with this IP21 conversion. Somebody configure something on the edge that they pipe to AWS that the sensor doesn't change for a week, and they've got it set to collect it every 1 second. You basically have a week's worth of data that doesn't really mean a lot, like you literally could have been saving that. And and it's funny because Ben Still, who works for me, we talked about this all the time, is with the Pi system and compression and all that, it gets misapplied so often. Is it worth it? Right.
Yeah.
And I'm a big believer in that. Yes, because it's going to matter. Right. And he's like, well, I've been around stuff where maybe it doesn't matter so much. So we come at it from a little different perspective, but then, we both kind of acknowledge each other's points. I think really the future of what this is going to look like is we have to have a tool like yours to be able to filter that data before it goes to storage.
Yep.
Right. And my suspicion is somebody's going to come ask you, you're like, hey, you're already the expert. Like, how do I pass the right data on to my however I'm collecting this data, right? That may happen to you. I could see that.
And we've already had, I'm doing a little bit of an exercise with a customer who wants us to have a look at even the influence of the interface. And so he's asking us to go in and have a look and compare the DCS data to the archived information. And so that's yet another, a lot of complications associated with going in and having a look at somebody's, production data on the other side of the DMZ. It doesn't, it's a really difficult thing to do sometimes, especially remotely. But there's clues in there that relate to data quality issues that could be addressed for sure. And again, what we're doing is we're looking at the raw snapshots as defined by the compression and exception algorithms implemented by OSIsoft, which happens to also pertain to all Rockwell implementations as well, right?
Correct,
So
yep.
the factory talk is the exact same as OSI soft. Some of Emerson's, I believe all of Emerson's are as
Yeah,
well.
Emerson's now a Pi.
Yeah, so, and so why did we choose OSI soft is, really they have the largest share of market of the
Yep.
data historians, and we can solve the largest amount of pain here with one implementation. So that's kind of where we started. But you are absolutely right. I believe that and especially with the Internet of Things, the Internet of Things is changing things dramatically on a daily basis.
Yeah, I think so.
People are considering adding tags where they're sensors where they never originally even conceived that they could have sensors. And now with communications the way they are, so this becomes an issue and or something that we can address kind of up front. So
Yeah.
it's a good point. I go back, one other discussion that we had, or that you just had or you had with Ben about, whether or not you should do that, when you should be doing this, and should you even be bothered with this or whatever. We've been in the data analytics business for, what is it, 23 years now, right? So, no, 23 years, 1997. I can tell you that when we do an analytics or a consulting work and doing analytics exercises for these customers, 80% of the time that we spend doing analysis is spent cleaning and manipulating data. And we wind up manipulating this data or cleaning this data in order to get it into a condition where it is a reasonable representation of what we're looking at. And what we are providing here with Compression Insight is a way to reduce dramatically that amount of manipulation of the data to make it so that it can be consumed by the end user. And I think you alluded to some of those in your examples, Jim.
Yep.
So we think doing this work up front with as minimal amount of resources as possible is extremely important and valuable for the end results downstream, where you don't have to worry, where data scientists and data analytics folks don't have to worry about whether in fact this is representative of what I need to be reviewing.
I agree. And those resources are expensive, and they're hard to a certain degree. They're hard to come by.
They really are, for sure.
So it's we need to maximize those resources, and and frankly, time series data is a little trickier to analyze from that perspective. So you're right. We need to make their job as easy as possible.
Exactly.
Because they're expensive. They could be working on a lot of other things, for us.
Yep.
Anyway, well, Paul, I thank you for this entire, series of segments here. I think, I hope people get an essence of why it's important. How do you get it right? And then, an idea of what your product is all about. How do they find you?
How do they find us?
Yeah. Now you're tucked away up there in Canada, eh?
Yeah. That's always been our biggest challenge. We hope to be getting the message out there on a broader basis. We're going to be we've been looking at some marketing campaigns.
Well, you have a website, right? That's kind of where I was kind of alluding to, right?
We do have a website. Yeah.
What is it? How do they find it?
So, well, how do they find us on our website? Is basically through word of mouth at this
No,
point.
But what is the website? What's the URL?
Oh, www.patterndiscovery.com.
Okay. And is there like an info, like if they don't remember exactly what your name is or how to spell it, is there a way to get
We have lots of information on the website. Compression Insight is there. It's one of our products. We actually offer a 14-day free trial of the system, full functionality. It is limited to 50 tags, but you will see everything that you're seeing here today.
Yep.
with the new 3.0 version. It's up there as of the beginning of last week. So it's all there, ready to use. Just go and visit the website, www.patterndiscovery.com, and see, you'll navigate to Compression Insight, and you'll see a little bit of a summary of what Jim and I talked about today, and you will certainly be able to download a full functional version for trial.
Very good. Well,
All right.
that'll help a lot of people. And Paul, again, I sincerely appreciate this. I think this is a timely and important topic.
Well, thank you, Jim. I appreciate it.
Absolutely.
Take care.